So we basically plug this in. It looks like I chose trial 1. Easy enough. So we know the rate is this, and we have each of the concentrations, and they are each to the first order. So boom, boom, boom. Did I do the math for it? Where is the math for it? Let's see. 2.4 times 10 to the negative third divided by 0.01 to the first divided by 0.01. There's the math for it. 2.4 or 24. Did I write something wrong? 10 to the negative third, 0.01. It's not 0.01, 0.01, it's 0.01, 0.1. So we get 2.4. Again, since this is for the both of these being first order, we get molarity to the negative first times second to the negative first. Basically, you would have molarity per second here. And since we have molarity squared on the bottom, because m times m, we cancel out the molarity on top. So we have the seconds and molarity to the first power on bottom. So that is the units for K. In experiment 2, what is the initial rate of decrease for F2? So we know the rate of increase for ClO2F. We know that for every 2 of these, we get 1 of these. So basically we start with the rate for the ClO2F. Every 2 moles per liter per second is 1 mole per liter per second for F2. So we get 4.8 times 10 to the negative third moles per liter per second. And then the new stuff we learned yesterday with the reaction mechanisms. We always start with the slow. If we take a look at this first one, ClO2F2, it is an intermediate. So we know that that can't be, if we look at our overall reaction here, it should be ClO2, 2ClO2 plus F2 yields 2ClO2F. So we need to cancel out the intermediates, and since the slow step contains the intermediate, we need to take and transition that into these two. Remember that if we do that, then the elementary reactions coefficients will be the orders. So ClO2 is to the first, it's 1 ClO2, so that is to first order, and F2 also to the first order. Well, that actually matches our KClO2 to the first and F2 to the first. That matches what we got from the experimental data. So that definitely is a mechanism that could work. It does say which of the following reaction mechanisms is consistent. So we're assuming this one won't work. Let's go ahead and see what we get here. Since F2 yields 2F is the slow, that means that we would have just rate equals KF2. The coefficient is 1, so that would be in first order. Unfortunately, we already know that ClO2 is also in first order, so this rate mechanism will not work. Boom, boom. Take a look at this guy. Is this the best version of this? I think it might be. So we take a look. Again, here we do have one that is consistent. This is 1984B. So we have one that's consistent. So we're able to do our old school method where we go 2, 2. 2 to the x equals 2, x equals 1. So then it looks like I did the rate for 4 and the rate for 3. And that gives us 1.5. And then remember, we're going to put these ones in here for that. And 0.6 divided by 0.4, also 1.5. So we get 0.6 divided by 0.4. We get 1.5x times 1.5 equals 1.5. We divide both sides by 1.5. We get 1. And what is the exponent to get us 1? Well, that is 0 order. This one's interesting because If X is in 0 order, anything to the 0 is actually 1. So you could also write this rate as rate equals K Y1. And what does that mean? Well, that means that the concentration of X is not going to have an effect on the rate. And why might that be? Let's just take a second, and we'll get these in a second, but let's go down to our reaction mechanisms. Hopefully this is bright enough. It looks dark for some reason. But if we take a look, for this one, we have both X and Y here, and M is the intermediate, and we know that we would get 2X plus Y yields Z. So this will make the overall reaction. The problem is that since this is the rate determining step, it's saying that X is first order and Y is first order. Well, that does not match our experimental data. If we take a look here, here is the slow. Y plus M, again, it looks like that we're adding the M here, and then M makes XX. Since this is the slow, we would get, let's see if I can do this. Oh, it's right here. We get the M, so we need to replace the M with 2 X's. So we would actually get something that looks like Y to the first order and X to the second order. Remember, we can't have this, M in here, so we'd have to replace it with this. So that's not going to work either because it does not deal with our experimental data. If we take a look here, Y makes M. M is an intermediate. M plus X then makes N, and then N plus X makes Z. This is actually pretty interesting because all we have in our slow is Y, which means that X would be not effective. The concentration of that would not be a factor for the rate. So that actually mimics what we see here. Even though we have it written here as 0, we don't see it here. And that comes up a little bit. If something is to the 0 order, that means it's probably not part of, well, it's not part of the rate determining step or the slow step. It is part of one of the other steps in the mechanism.
So really quick, when you were doing number 2,
yes.
So if we have a fast step then a slow step, we have to replace the intermediate thing with like the products that make it.
Well, the thing is you may not have to, but yes, like well, this is the this is something else that comes in, and then we would replace it with these 2 things. Yeah, this one doesn't work on several reasons.
Okay.
Yeah.
So should we do that every time there's a fast and a slow step with an intermediate?
Well, I mean, just like the ones we did yesterday, it all depends. If it is fast and then slow, yeah. If you have something that is not from the actual overall reaction, okay, then you cannot have that in the rate law. You need to replace it with the things that are in the overall reaction.
Okay. Thank
you. What's this? 1 is done. First order and X is in. Oh, this is explaining why each of these are not possible. So X is in first order, as I said. It doesn't fit because we have X in second order, and it shows Y in first order and X in 0 order. All right. Let's try B. Calculate the specific rate constant. Where did I do B? Ah, just put it right here. I think that makes sense because it's just time to the negative first, which is a unit for a first order reaction. So basically, I'm not sure which one I picked, but I picked one of them and then plug that in. This would be 1 and this would be 0.1. So we take the rate divided by 0.1, and that does move the decimal 1 place. So that is K. And then C. C is kind of the one that, well, it's different than I think most of the stuff we did. It does kind of take in if you remember, and I don't know what Mrs. Cotton used, but some people call them rice tables, some people call them ice tables, and some people call them BACs. Basically, rice stands for the reaction, the initial, the change, and then equilibrium, or the event after the event. BAC, if you're watching videos or whatever, that would be before. I'm sorry, BCA, before, change, and after. Basically, what you do is you look at initial amounts, X, Y, and Z. We have nothing. So these are the initials. From the reaction, we know that the change, these are the reactants, they will be used up. This will be used up twice as fast as this. This is the product, so this will be added. And this is after or at the event, at the time of the event. So we do know that Z is equal to 0.2 molar after the reaction proceeds. So basically it says how long must the reaction proceed to make this. So that's the after effect. So if we went from 0 to plus to 0.20, that makes X 0.20. Not really worried here because they say how long must the reaction proceed in order to produce this. Not really worried here about this one because we know that's in a 0 order. So we want to focus on the Y here. So if we take a look, we start with 0.6 moles per liter of Y given from here. We know that it's a 1-to-1 ratio, so we're going to lose X, which we determined X to be 0.20. So we take the 0.60 minus the 0.20. This is our final concentration. This is our initial concentration. And since this is first order, we can use the integrated rate law for a first order reaction, where the natural log of the final concentration equals the negative slope times the time plus the y-intercept or the initial concentration. Since this is addition, we can subtract the natural log of y from both sides. And if we then have the ln of y minus the ln of y naught, we can turn that into the ln of basically the concentration at the final divided by the concentration of the initial. We do know the K because we solved that right here. It is negative K. So you take in your calculator 0.4 divided by 0.6 log of that, the natural log of that, and then we divide that by, notice that negative, so we make sure we got the negative 0.007, and that gives us 57.9. What's our unit for K? Per second. Since it's on the bottom of the bottom in a sense, that is 58 seconds. Again, I think, I don't remember who I was talking to. I talked to a few of you yesterday. But you can see out of a lot of these different tests, I wanted to make sure I showed you that. 1991 and 1984, it doesn't come in many more of these, but this is something that if this does come up, and I don't like this aspect, if this does come up, that means that your order is going to be messed up for basically the rest of this. So if you get fouled up here, then that's going to affect a lot of what you see below probably. This one maybe not as much, but yeah, you could get screwed up on this one, but I mean, you'd still be able to do C at least. You wouldn't be able to do B. So wanted to make sure that I showed you that method. I think it's probably best looked at here. The other thing is, this was the only example of this occurring that I could find. Again, most of the time you don't actually have to calculate these things, but maybe like you need to make sure that you can if needed. But a lot of times it basically wants to talk about this, like making sure that you understand that this reaction, or this equation is for a first order. All right, so let's take a look then at the review real quick. I actually expected to have a little more time with it. So here's the deal with this. You do have access to it. The problem is that it does contain, and I did this on accident, but it does contain some questions that they won't allow you to look at without a secured browser. So if you have your Zoom on a different computer, then you can click on this. You should be able to click on it right here and it take you to it. Otherwise, you can log on to AP Classroom and get it from there. But if not, let's go ahead and just talk through these real quick. And hopefully I can get most of it on here. Can you, does anybody have their cameras on? No? Just give me an audible yes. Can you see the full screen on that? Does it look decent? Question
Yes.
one. Okay, thanks. All right, so if we take a look, they give us the actual rate. They say rate equals K, X to the first order, and X. So this means that, as we talked about before, that means that Y is in zero order. So Y is not going to be part of the rate determining mechanism, right? It's going to be lower. Looking at these two mechanisms, that doesn't help us really, because Y is, separated through all of these. One thing we could do is we could go through and mark out our intermediates. So if we go boom, we could lose these two X's here. And then we have X2 and then Y2. We look XY2 is an intermediate, so that would get canceled as well. And then we get X2, Y2. So I know mechanism 1 works. So if we look at our answers, only mechanism 1, well, I don't know if mechanism 2 works. And if we take a look down here, so basically I've already canceled out D and B. So, and this is something that, we've kind of made this then, 50% now, right? So it's like kind of like a true false question. We know it's either A or C. Let's take a look here. Now, looking at the slow reaction, we definitely know that we could make this because the coefficient right here is 1. So that will make that rate law. We have to analyze this mechanism to see if it's actually functional. So here we have 2x, so we could cross out that 2x. That would leave us x2. Y2 does not cross out. If we take a look here, y does cross out and xy does cross out. So those are intermediates. We've already crossed out this x. X2y crosses out. So this one looks like it'll work too. X2 plus Y2 yields X2, Y2. So it looks like we would have to choose C on this. Both those mechanisms work. The energy diagram for the reaction X plus Y yields Z is shown above. The addition of a catalyst to this reaction would cause a change in what? Well, let's identify these. Can anybody tell me what this I is?
Activation energy.
Very good. So if we add a catalyst, will it affect activation energy?
Yes.
Yeah, we know a catalyst basically finds an alternative mechanism or pathway, which lowers the activation energy. So currently we have A possible and D and E possible. 2, what is this considered?
The activation energy for the reverse reaction.
You're awesome. Would that be affected by the catalyst?
Yes.
Yes. Well, now we have a possibility of D and E. What is this called?
It's like the delta E.
Delta H of the reaction. Is that affected by a catalyst?
No.
No.
So we would have to go with E here. So it would affect 1 and 2. Free chlorine atoms encounter O3 molecules in the upper atmosphere. The following reaction mechanism is proposed to occur. A lot of information on here. Here we have the slow step. So if we take a look, we have ClO. That's going to be an intermediate. And then we get 3O2, which makes sense. And we have 2O3. What is Cl here?
Catalyst.
Catalyst, very good. So what that's going to tell us, if we take the slow step, we have O3 to the first order and Cl to the first order. Remember, if the catalyst is in the slow step, it needs to be in the rate law. So if I'm looking at this correctly, that would be B.
I forget. How do you know if it's a catalyst versus like an intermediate?
Yeah, so if we look, an intermediate is going to cancel out. Remember, so we have it on the product side and the reactant side. It's a catalyst if it's used and then it's reformed here. So remember, these do go in, this is the first step and this is the second step. So this is the first step and we see the catalyst and we see it being reformed in the second step. Here we see this being formed in the first step and then getting used up in the second step. Is that good?
Yeah, thank you.
You're welcome. Same reaction. We have a delta H being negative. Like I said, there's a lot of information here. Which one definitely can it be? If we look here, this is showing what type of reaction?
Endothermic.
Endothermic. So D is definitely out. We do have this mechanism that has 2 steps. So which of these energy profiles also would not be possible?
A.
A, because we don't have the 2 humps. Here we have our reactant, and here we have our intermediates, and here we have this being exothermic, as we said. Which of these 2 do you think? What's the difference between these 2? Well, if we take a look here, for our intermediate, we go way down here, and that's going to be a problem. We're not going to lose more energy than our products are going to be. So this is going to be the one that we would look for. Just a little subtle difference there. This is more like the problems that I'm talking about by being able to recognize what you should be looking for to determine order from a graph. So if it's second order, way too much highlighted there. We said that basically this is nothing. Concentration to time, the slope, this is the concentration of the reactant, it's decomposing, so the concentration of that should go down. So this is nothing. This would be if it were 0 order. Out of these 2, we did say that since this is second order, our slope is going to be positive, and we do take the reciprocal of the concentration. So D is the only one. If you remember that CLR, the R tells you for second order, it's reciprocal. And that is the only one that has a positive slope. Basically,
So
we're squaring that concentration.
if 1 over X is increasing, that means that X is decreasing, right?
Yes.
Okay.
And it is squared here because of the second order. That's why we get a positive slope as well. The oxidation of iodine ions by arsenic acid in acidic aqueous solution occurs according to the stoichiometry shown above. The exponential rate law is, so they gave us the rate law. So there's a lot of different things here. They could ask us, what's the overall order? Blah, blah, that type of thing. Let's take a look here. According to the rate law of this reaction, an increase in concentration of hydronium, well, it is first order. If this were zero order, an increase in concentration would not have an effect on the rate. So if we do increase this concentration, the rate should increase. Not valid for this. Not valid for this. Neither the rate nor, yeah, not valid for this. What's that one more time?
If it was a second order, would it be any different?
No, second order would also be, the concentration of it would also increase the rate. The only one that it wouldn't is zero order, because then whatever this concentration is, it becomes one automatically, right? Which of the following best helps explain why an increase in temperature increases the rate of the chemical reaction? Monk, you're always good at this.
What? Oh.
You love the temperature things, don't you? You always.
Oh, not gonna lie, I wasn't really paying attention.
What are you doing instead of no? So if we increase temperature, we know that's going to increase collisions. We also know that that's going to give more of overall number of particles is going to have, well, how should I say this? A higher percentage of the overall particles is going to have the activation energy. Increasing the temperature itself does nothing to the activation energy. It just makes sure that more of the particles will have that activation energy. So at higher temperatures, again, remember you have to look at that Maxwell curve, and your average temperature is much different than all of the particles, right? If you have a higher temperature, a higher percentage of the particles have that higher, have higher temperatures. But that doesn't mean every collision is going to result in the formation of product. So the only one that could be is D. Higher energy collisions happen more frequently. Notice we know that collisions would happen more frequently, but also higher energy collisions would happen more frequently. Factors that affect the rate of a chemical reaction include which of the following? Factors that affect the rate. So frequency of collision, more collisions, higher rate, less collisions, lower rate. Kinetic energy of collisions, just like we said, that Maxwell curve, it's going to change the percentage of particles that have higher energy. Orientation of a reactant. Yeah, that's also going to do it. This is something that we don't have a lot of ways to change that orientation because they're basically just bouncing and bouncing and bouncing. One way that we can do that, and it's kind of a cheat, but it would be like the catalyst. But all three of these definitely would affect the rate. These two we could, we'd have a better chance of changing. A frequency, we give it higher concentration, or we turn up the temperature. Kinetic energy, we turn up the temperature. Orientation, it's hard to control that. Like I said, you'd have to probably have a heterogeneous catalyst, something that they combine to and line up better. C2H4 is reduced by H2 in the presence of a solid, oh, here we go, solid platinum catalyst, as represented by the equation above. Factors that affect the rate of the reaction include changes in partial pressure. Remember, gases, if you change the pressure, that's like changing the volume, which changes basically the frequency of collisions. So yes, that would be a factor that would affect it. Change the particle size of the platinum catalyst. Again, they're just looking for factors that affect it. If we made bigger particles of platinum, there would be less of the binding sites for the catalyst. If we ground that up, we would have more binding sites for the catalyst, so that would increase the rate. So again, yes, if we change the particle size, it's going to change it. Changing in temperature, yeah, we know that that changes K. So again, this is going to be 1, 2, and 3. If the oxygen isotope 20 or oxygen 20 has a half-life of 15 seconds, what is the fraction of the sample after a minute? And here's the deal with these. Keep in mind during the actual AP, the multiple choice questions, you are not to use calculator. So if we take a look, what do we have? 4 15s in 1 minute. So basically that's 4 half-lives, right? So if we go 1, actually if you go 1, 2 to the 4th, that would give it for you. 1 over 2 to the 4th, because we have 4 half-lives going on. So it'd be E116. Or you can just do it in your head. After the first one, we have 1/2. Then we have a half of a half, which is a 4th. Then we have a half of a 4th, which is an 1/8. Then we have a half of an 1/8, which is a 16th. And that's our 4 15-second intervals. Mechanism, a reaction mechanism for the destruction of ozone. They like this one. It's represented above. NO is best described. All right. You get it? Is who asked about the intermediate versus a catalyst? What is NO going to be in this one? Is it an intermediate or is it a catalyst? Louder?
Catalyst.
Very good. Yep. We know that it is used up first and then it is reformed, meaning that it's not absorbed into the reaction or not used up overall in the reaction. Decomposition of H2O2 peroxide is represented by the equation above. A student monitored the decomposition of 1 liter sample at a constant temperature of 300 K and recorded the concentration of H2O2 as a function of time. Results are given below. 200, 400, 600. We're not losing half on that each time. All right. So this is a weird one. Which of the following statements is correct about the data? The reaction must be first order because there's only 1 reactant species. That's not necessarily true. It could be second order. The reaction is first order if the plot of ln versus time is a straight line. What a weird question. Let's go through the rest. The reaction is first order in the plot of 1 over. Well, right there, this part is false. It would be second order if this plot is a straight line. The reaction is second order because 2 is the coefficient in the chemical equation. We would need the mechanism and we would need to have the slow step visible to determine that. So it can't be this. And that's, I don't like that question, but it's like, if you did this and this occurred, then you would know this. Basically, all it's doing is asking you if you know that a plot of the natural log of peroxide versus time is a straight line. And that's all we got time-wise. So you're more than welcome to start the progress check, as I said today. It's not due until, I believe, Tuesday. I'm using Monday's whatever time to give you guys that. To tell you the truth, I think what we'll do is we'll hold off on doing thermodynamics until next Tuesday then. What we'll do is we'll come in here, we'll finish 12 through 19, then I'll let you guys go get started on that tomorrow and set you up, and hopefully then you don't have to use any time over the weekend or anything. Questions for me today? Somebody write down that we're starting on 12 of 19, please. And again, you have the ability to go through that on your own, but it is, as you can see, it is blocked off as needing a private browser. Have a great day, guys. If you have questions, remember my office hours are from 10:30 to 11. Adios.
Thank you. Have a good day.
Hey, thank you.